for the benefit of the class on Friday, I'm going to of the problem that class. I'm actually going to class. So here's the 10 kilogram box on a ramp, slope of 30 degrees horizontal. Coefficient of static friction between the box and the ramp is 0.4. Coefficient of kinetic friction is 2. Front edge of the box is 2 meters from the end of the ramp. Ends at rest. How long will it take the box to slide to the bottom? So, to begin this, as we begin problems, we're going to picture our ramp. We know that there's a box up here. The box has a mass of 10 kilograms. Front edge of the box from box begins. And we know that we have friction between the box. S for the static friction. Or remember, the static friction between surfaces. There's no motion. So when the box is at rest, that is the coefficient of static friction. We call this the coefficient of kinetic friction. That is 0.2. The idea here is that this box isn't moving. We don't actually know if it's to move. We've all seen something at rest on the side of a hill before. So what we have to do is actually do a comparison. Say how much gravity pulling down on this box, and that enough to overcome the pull of the force of the static friction. Static friction is bigger than gravitational force pulling the box down the hill, then the box will be at rest and it will never get to the bottom of the hill. But if it is in motion, then we can't use static friction, the box is in motion, so we have to kinetic friction. Talking about forces, that should be a good indication that we need to look at a force diagram. A problem where there are forces. So, there's my box. We also know N, that's the triangle. Go to our force diagram, put in a dotted line, represents our surface, and we're going to declare this our horizontal axis. Put in a dotted line perpendicular to that, and we declare that to be our vertical axis. Now, get this 30-degree angle in. That's actually a fairly important number. I don't want to focus that range. Okay. Get that 30-degree angle. So I'm also going to put in a dotted line representing horizontal and vertical. Now I need to transfer this 30-degree angle here. This line represents my surface, represents horizontal. I know that there's a 30-degree angle between those two things. So fuzzy. Doing a piece of geometry, 30 degrees here, also be 30 degrees there. Vertical angles. Geometry, here's horizontal, here's vertical. That is 90 degrees, that's 30, so that must be 60. Our x-axis, there's our y-axis. Another 90 degrees, that's 60. Angle must be 30, 60, 30, all the way around. So we know all of these angles and that we need. Not horribly clear. Well, I'll just try to write bigger. All right. Let's look back at our picture. There's our system, the box. We have a couple of interactions. Entire Earth interacting with the box. have the ramp surface. Remember that surfaces are capable of exerting they always exert the normal force, which is perpendicular to the surface. They sometimes exert a frictional force. In this case, it most certainly exerts a frictional force. We have all kinds of information in the problem telling us that. So we put in these forces. Earth, gravitational force straight down. Surface exerts normal force at 90 degrees to the surface. Remember that this diagonal dotted line represents our surface. So our normal force is straight up from that surface. We then have a frictional force that we have to deal with. The question is, frictional force up or down the hill? You have to think, what is the box going to do? It moves. That's quite clearly down the hill. The box is going to slide down this hill. Friction, being a resistive force, is going to be up. Our frictional force. Now that we have our force diagram, look at our Newton's second law relations. F net in the x direction has to be equal to s times the acceleration in the x direction. F net in the y direction has to be equal to m times the acceleration in the y direction. Draw vectors. All right, well, looking at our force diagram, our x direction is not horizontal in this case, it's along our surface. Our y direction is in this way. Well, gravity is not behaving itself, so we need to break this into the color. Going to the end of our force vector, I'm remembering that the vector we are breaking components has to be the hypotenuse of our right triangle. One component, there's the other. 30 degrees up there. This is then FG parallel to the x-axis, so we call that FGX. This one is FGY because it's parallel to y-axis. Now we have 4 forces. One has been replaced by these 2. 4 forces which are all parallel to one of our cardinal axes. Come over here and write this out. X direction, we have FGX down the hill, we'll call positive, minus our frictional force up the hill, that has to be AX. In our Y direction, we have 2 forces. The normal force up minus FGY because it is down. That has to be equal to m times acceleration in the y direction. But we know something about this. So that box, somewhat may, is not going to accelerate perpendicular to the surface. It's going to slide down the surface. Not up, not down. Down the ramp in this direction. That tells us that the acceleration in the y direction is 0, which is quite nice. So this whole thing goes straight to 0, which tells us an important piece of information. Normal force equal to magnitude equal to FGY. We have to make sure we're careful with direction, but magnitude, these two things are exactly the same, which we could have filled in right off the bat up there. We knew that was true from the beginning. Okay, well, can't do much with this, so let's see what else we know. Oh,